Hi, I want to use this tutorial to sum up some key points about the normal force. And this builds from these practice problems you did with the cat and pushing down on the cat with an applied force while it's resting on the floor, and then trying to lift up on the cat when it was resting on the floor, and then the first situation, which was just sitting there doing nothing. Okay, there's my cat. And then we also did in class some elevator problems. And I'm just going to draw right here real quickly what was going on. We had somebody in an elevator, okay, that represent the elevator. And on one of the problems you did, the elevator was accelerating down. And I asked you to solve for the normal force. And what I want you to realize, if you go to the problem, is that the normal force was less than the weight. And if you do the next problem, so here's another elevator problem, and the elevator was accelerating up, you would find the normal force was greater than the weight. And how much greater or less depends on how much acceleration there is. That's really a very important point. If the elevator was moving up or down where the acceleration was 0, but it had some velocity, we would find the normal force equals the weight. So what I want you to notice in this situation and this situation, normal force equals the weight. What's true about this situation? There's no other vertical forces except the normal force and the weight, right? So if I draw an FBG, and this is for number 3A, that's all there was. In 3B, when we're pushing down on it, right, there was an applied force, there's still gravity. The cat didn't accelerate, so the normal force had to be really large to counterbalance both. And we see something similar in this situation here with the elevator. When you're accelerating up, the normal force has got to be bigger. It grows where the FG doesn't. FG depends on your mass. It's not going to change regardless of what the elevator is doing, but the normal force will respond. It has to be bigger than the weight in order to accelerate you up. And then in the third situation with the cat, you had the applied force up. It's still on the floor, so there's going to be a normal force up on it. But since the cat's not accelerating, those two have to balance FG. FG didn't change. So the normal force is going to drop because the floor is not supporting you as much because somebody else is helping to support the cat. And we see something similar in this problem where when you're accelerating down. When you're accelerating down, the normal force gets less because the floor, oops, got that in the wrong direction. The floor doesn't need to support you as much. Okay? And that's a little bit more abstract. You're still the same weight down, but the normal force is going to drop. So, what's this all have to do with? Well, this goes to the very last question we asked in here, is when you stand on a bathroom scale, what would be registered, the cat's true weight or the normal force? The true weight of the cat doesn't change regardless of what you do to it because it depends on the mass and the planet pulling on the cat and the earth. However, the normal force changed. And you can imagine if that cat were sitting on a scale, when you push down on the cat, the scale would go up. And when you lift it up on the cat, the scale would go down. So the scale reads the normal force. And that's really important. So a bathroom scale does not measure actual weight. All right, you say, well, that doesn't make sense. When I stand on a scale, I have to weigh myself. But that may be true, but you're really not measuring the weight. You're measuring the normal force. Okay, and that's what we call your apparent weight. So sometimes normal force is called the apparent weight because that's how you literally feel. That's what your weight appears to be. And so what I'm getting at is you can change what your weight appears to be depending on the situation. That's what the problems above are illustrating. Okay, so as such, your apparent weight, so when I use that term, don't confuse that with the actual weight. The synonym with apparent weight is normal force, okay, can be altered. So what are the three situations where you can make the normal force different than your weight? We've already talked about two from above, and there's a third one we'll eventually look in more detail. Okay, so the first situation, other vertical forces are present. So that's what the idea was behind the cat. We were pressing down on the cat or we were lifting up on the cat. So those other vertical forces made the normal force change, alter to the situation. When you lift up, the scale would go down. You would feel lighter. Okay? If someone pushes down on you or something unforeseen pushes down on you, you would feel heavier, and the scale would register that. The second one is pretty important, and that's what the elevator problem was about. When the frame of reference is accelerating, there doesn't have to be any other forces. Accelerating, okay? And the elevator is a classic example of that. So if I go to the force diagrams here and here, okay, because we're accelerating, the normal force can't be equal to the weight. Otherwise, you couldn't accelerate. They'd be balanced. We don't have introduced any other extra forces here. There's no other external object that is applying that. So the implication of that is, when you're in this situation here, accelerating down, not only was a scale reading, if you were standing on a scale go down, you would feel lighter. If you had no idea that the elevator was accelerating, you were just in the elevator and you say, whoa, I feel lighter than normal, it could be because not you lost weight or mass, it's because it's accelerating down. And if it's accelerating up, you'd feel heavier. And so a natural question is, how much heavier or lighter, and what's the limit you could take that? I'll get to that in a second. So the last situation we'll discuss more is when you're not on a flat surface, or put another way, when you're on an inclined plane. Okay, there's no way, if I have an inclined plane like this, the normal force by definition is perpendicular. The weight is always down. There's no way those two can balance because they're not in the same direction, or they're not in the same plane. Okay, now, when you don't have any of these three situations, that's what I'm saying right here, then the normal force will be equal and opposite to your actual weight. Okay, so imagine you're standing on a scale. It's on a flat surface. So we take away criteria C. All right, there's nothing. You're not leaning on anything else. Nothing is pushing on you, external to you. So that's criteria A. And if the scale isn't accelerating, which it usually isn't if you're in the bathroom or somewhere else in your house, then we can say that the normal force, which is going to be up, and the weight, which is going to be down, have to be equal and opposite. Okay, now I'm going to add a fourth bullet here. And this is something I'll demonstrate to more in class if I haven't done so already with some videos. And that's what happens, what is the normal force when you're in free fall. Okay, so if you were to draw, here's a scale, let's say you're on some surface, an elevator, let's say, and it's accelerating down, that's free fall, and we know that the acceleration equals g. Okay, if I were to draw a force diagram, well, you might be saying, oh, okay, I'd have gravity down and I'd have a normal force up. And you should be pretty sure by now this is going to be less than the weight. So how much less? What's it going to be? Well, conceptually, free fall, the word free means the only force acting on you is gravity, so the normal force would be zero. That's the easiest way to approach this. The second thing I could say is I could apply the second law to this, or I could say my net force is Fg minus Fn, and I could set it equal to the second law of motion equal to ma. Well, if you're told A is equal to g, then that equals mg. And we know how to calculate the weight. Your weight is mg minus Fn equals mg. Do the algebra, you see the normal force equals 0. So that's pretty cool. So if you're in an elevator that's in free fall, you would stand on a scale, it would read 0. What does that mean? You're weightless. You would literally be weightless. So if you let go of a ball in an elevator, it would hover right in front of you because it's already falling. And if it's already falling, it can't fall any faster just because you let go of it. So when we talk about astronauts in orbit, and you see video of the astronauts in orbit and things floating, it's not because there's no gravity. In fact, there is plenty of gravity there. It's simply because everything's in free fall. And when you have free fall, there's no normal force, so you don't feel any weight. So you're literally weightless. Conversely, if we could accelerate up at g, so let's say we were accelerating up, we could work out the algebra, and I'll let you do that. You would find normal force equals twice your weight. You would feel twice as heavy. If you're on a scale and you normally reads 100 pounds, it would now read 200 pounds. And you, if you didn't know any better, you'd say, wow, I've gotten really heavy. You'd be harder to walk, it'd be harder to jump. All those things that your muscles and bones are used to would feel twice as heavy. Okay, so really, really important, the normal force, besides just supporting you, it's what you actually feel as your weight.